For those of you who happen to have been at the Plug Fest in June at Microsoft, there's a lot of the same information in this. So just so you don't get too disappointed on that. But it's still a pretty good introduction to what is Azure Files, and then specifically what sort of things we've kind of learned that we didn't anticipate, but that ended up being problems that weren't really problems. That a lot of it has to do with the massive scale and just different expectations that people have of the web. This is the public cloud. This is a survey of just the topics to cover. First, a kind of a history of Azure Files and why we did it, and this probably go really quickly over SMB since this whole room is very familiar with SMB. The design of how we did it and then what we've learned actually doing it. Protocol history, you're probably all familiar with this. It goes a long, long way back. SMB3 was a milestone for us because the persistent handle support and the continuous availability that allowed really made what we were doing feasible. It wasn't really feasible before then to have a realistic customer experience in terms of handles reconnecting and being seamless from the application point of view. And also another encryption as well that enabled some really neat scenarios where you can now net use from anywhere from the world. So from home or wherever, anybody who doesn't block 445 outbound, you can then see your network shares. One interesting thing is the protocol documents that Microsoft actually had to do for the EU Commission ended up actually being very useful. And so surprisingly, so even though it was very difficult for Microsoft at the time to write all these docs, it turns out that having all this information in more than just one or two people's head is actually really, really useful even within Microsoft. And so I was able to go and pretty much implement it just based on doing this. Again, it goes very technical into the what's and not the whys, as most protocol documents do. But still, it provided the bulk of the documentation for everything that we did to build this. Azure Files, one of the things, actually, in the later slide I get into this, but it's based on top of Azure Tables and Blobs. It is not like running serv2.sys on Azure. And as I said in the last sentence, that's the fundamental thing. People often thought, oh, you're just running serv2.sys on Azure. Like, absolutely not. It's not based on even a real file system. It's an object store underneath it. And the SMB2 spec actually talks about object stores, and so it was actually really natural for us to implement it that way. It's completely new, just implemented using Azure Tables for metadata, and then Azure Page Blobs to actually store the file data. And because we'd already had all that infrastructure to make those things very durable and resilient, and to power outages even, or to especially just network disconnects or a service going out, that just seamlessly flows. And so as things happen on the Azure, internally on Azure, they're pretty much invisible to a user who's actually using Azure Files. Currently, there's SMB 3.0 support with encryption and persistent handles, 5 terabytes per share. That's the implication of right now we have a single partition per share, and the partition is a concept within Azure Tables having to do with atomicity. And so we have this one-to-one mapping to partition shares today, anyway. IOPS, 1,000 per share, that's an arbitrary limit. That's just so that we don't have too much of a noisy neighbor problem and that people can create multiple shares. But because a single share is on a single partition, we didn't want too much of an impact on other neighbors. One of the issues in the public cloud is what's called the noisy neighbor problem, where you happen to be on a machine with someone else who's being very active. And that's one of the problems that we've experienced. So that's just an arbitrary limit. Most of Azure Files, Azure Tables and Blobs started using a REST interface as kind of the new modern way to access data in the cloud. And so we wanted to provide this common namespace so that you could actually access the same files via both SMB and REST. One of the problems with that is that over REST, it has to be a valid HTTP string. And so that implies additional character limitations and also some path limitations and number of components in the path. So we actually had to use the lowest common denominator. Windows allows pretty much, well, the SMB spec specifically, anything, right? It's just 32,768 characters. And actually, they're just WCHARs. Now, there are some limitations beyond that due to some mappings and what's legal in NTFS. But that was wide open. So really, it was more HTTP restricting the namespace so we'd have a common denominator between REST and SMB. And so far, it hasn't been much of a problem. We've had some issues with our TCP/IP.sys driver where there was some things were being more stripped out than they technically had to be. So we're working on getting those. But that's been some implications for some Asian character sets. We support Linux because we don't care, right? We're just an SMB server. And this is currently the status of the SMB3 support, as Steve was just talking about. The encryption is in on, looks like just the Ubuntu server 10.04. This is as of actually June, so it may actually be a bit better now. But it's marching forward. The code is all there and checked into Linux, so it's just a question of other distros adopting it. Again, persistent handles is very important, and I'll get into persistent handles a bit later, because without that, you don't really have a very good customer experience. And encryption allows you to access Azure Files from outside the data center. If you're running within a VM inside an Azure data center, you don't have to use encryption. You can just talk directly to your share without encryption. Though we still sign it. We require either signing or encryption, just for data integrity. But unless you're actually going outside the data center, it doesn't have to be encrypted. Oh, it does have encryption. Okay, all right. And this is the kind of neat, completely new with, in a way, Azure Files, that this ability that you have now anywhere in the world, I mean, from home, from wherever, to basically access the same data share from any point and have all the leases work, all the op-block sharing modes, multiple people on all different continents all accessing the same file at the same time. And with all the coherency that SMB's rule, the rules in SMB over leases guarantees, that all just works. So it's a pretty neat thing having all this completely distributed users from all over the world be able to access the exact same files and have a completely coherent view of them. One of the caveats to this, as seen in the bottom, is that port 445 outbound has to be unblocked. And this is a problem especially after the WannaCry problem, because even though that only affects 445 inbound, you have to be listening on 445. A lot of network administrators will just hear the word 445 and just close off and just not allow it. And so a lot of it has to do with educating them. There's a difference between inbound ports and outbound ports. So it's much more difficult than you might imagine. And some large ISPs, Comcast blocks 445, but AT&T doesn't. So it's just a question of your ISP whether they block it or not. And hopefully that situation will get better over time. But WannaCry didn't help. A demo. Okay. So I'm going to hook up my mouse here because it's much easier to do it. And by the way, I want to thank Jeremy for the use of his cell phone, because while everything was working perfectly with the conference Wi-Fi this morning at 7 o'clock in the morning, as I was testing it this afternoon, it was dropping packets. And this laptop that I have to use, which is my issued ultra-secure laptop, if it doesn't, once it loses its VPN connection to Microsoft, it shuts off the network completely. And then it goes through these cycles like 2 times a minute of like on and off, and it was just not working well. So right now I'm hotspotted into Jeremy's phone, which is nice. And if you can see here, the actual talk that I'm giving is from the Z:" drive, which actually is an Azure file share. So I'm actually giving the talk from an Azure file share, which I may not have done had I not had a more reliable network. And it's just, here you go, you see my share name there, and it's just basically a normal normal Windows share. No, I don't want to use the store. Okay, well, it's supposed to open it. Oh, it's because it's a PNF, so it doesn't know to open a notepad. Anyway, so this is just generally, you can change stuff and change notify is, you'll see here that the time just updated to today. I can go down to so I can delete this 3 guy, I guess. 3 where to INF. And then it just boom, disappears. So change notify was one of the funner things to do. But it basically implements byte range locking, nearly everything that's in the actual MSSMB3. Some of the more exotic features of NTFS we don't do yet, kind of on an as-demand basis. Because again, we're not based on NTFS, so we basically have to reinvent all those features if we need them. So it's basically due to customer demand. Things you're thinking about, things like hard links or name streams, and Jeremy said, please don't do name streams. So it's kind of just your normal file share. I should probably do something a little bit better for that, but it gives you an idea of what's going on here. It's just basic normal file share. And resume from current slide. Okay, so the reason why we did this was that people wanted to move to the cloud, and this is the only marketing slide on the whole thing, so that they could basically take workloads that they had and kind of just basically run them immediately. And so if you had an existing enterprise app that was written 25 years ago or something to like the C runtimes, that's that's difficult sometimes to port to a whole REST and rewrite the whole thing. But if you know that it works fine, then in theory you can just go and point your share to the cloud and it should just work. There are some caveats to that, that kind of the latter part of the talk goes into things that we've discovered that weren't quite as simple as we thought they would be, or things that people hadn't considered. And because they can also stage workloads, even if they're by having them first having their application servers in their business and just having their data in the cloud, and then if that works well, then it could eventually move even the application servers into the cloud. So they're completely hosted offsite. And again, REST, it's considered a future protocol. Statefulness has a lot of benefits. People like files. Who was saying that? It was Steve Frenchman was saying people really like files. And so they have a long history and they're very useful. There are cases though where the statelessness of REST in terms of scaling is really nice as well. So again, you can basically do both. So you could have an existing vertical app that you basically run against Azure Files, and then slowly over time you can change it over to REST, and the data doesn't have to move anywhere. It's just sitting all right there. And so these are all just the Azure Files REST interfaces. So where we put all metadata is in these things called Azure Tables, which are just NoSQL tables that have a bunch of rows and a bunch of columns, and you can generate keys. And we basically generate partitions at the point of the share name. And so within a particular partition, that is at any given time hosted by one server. So the metadata. And what that allows us to do is to do ACID transactions across not only that row, but then we can also, you can make multiple rows that are at any given time owned by one server, and then you're able to just go to do a single transaction easily across multiple tables, which correspond to the different sort of things that you need to keep track of in a file system, like handles and files and file locks, change notify requests, change notify events, and all those things that you need that generally you'll have in-memory structures for on a normal file system, instead are all durably committed to these Azure tables. And so an implication of that, which I think you can see right away, is it's a lot faster to update a counter in memory than it is to durably commit 3 copies of something in a data center. And so that has some implications, especially on metadata performance, which we'll get into later. And the way I mentioned about the special tables that can scale multiple tables, we call them nested tables, which isn't a great name, but what it means is that you have a single set of tables that are all co-located within a partition, so that we can do transactions across all of them. We can do an ACID transaction across all of them in a very easy way. These are the Azure File Share tables that we generally, these are some of the most important ones. There's a total of about like 8 or 9 now that we actually have. But the idea is that you have a file that's just your files. And we have different hybrid rows in that for namespace and blobs to make dir faster, basically. And also to be able to go and do the real motivation. The one thing we tried to only go with the file-based namespace, and it turns out directory rename was our undoing. And we just couldn't get directory rename to work without having a separate namespace table. It's just, directory rename is evil, basically. I wish we hadn't done it 28 years ago. The page table is where all the data is stored. That just keeps track of where in the low levels of Azure Files, when what are called streams, the actual user data is stored, and that tracks on which multiple servers they are, so that we can find the data to read or write it. Handles are just handles. Leases are SMB leases, which is a buffering optimization. That it's a very large optimization, so it's very important to do it. Change, notify, and byte range locks, and those are kind of the heavy hitters of what you see in terms of the different tables that we use. Namespace requests are more expensive for us than on NTFS, because if you think about doing an open on NTFS, after the first few opens in any given directory or something, chances are it's faulted in those pages of the MFT, it's faulted in those pages of the directory, so you might pay a bit of cost on a few disk accesses opening the first file in a directory, but then it's just cycles at that point. And so what NTFS can do in a few microseconds, a handful of microseconds, for us, because we have to durably commit open counts and creating new handle rows, it can take milliseconds instead. And closes are particularly nasty because we defer a lot of updates to close. This is when we do our change notifies, this is when we update our timestamps, that's when we delete files, which has been a problem that I'll get to later. And so those can be much slower on Azure Files than on a local, especially a local volume, but even talking to a local server2.sys, a normal Windows server. Because Windows Server, especially if you don't open the file if you don't open the file right through, it's not durably committing anything either. And even its open counts are all still in memory. If you copy a directory to a Windows server and then pull the plug in the server in the middle of the copy, what actually made it to the server is not exactly deterministic. You'll power it up and see what made it and what didn't. Whereas if you do the same thing on Azure Files, the last write that act, that is there for sure. The last create file, it is there for sure. And that's kind of a big difference. But it's very important for the sort of enterprises and the kind of applications we're targeting is that kind of robustness. This is a kind of a conceptual idea of how hardware is oriented within Azure Files. We have front-end nodes, which is actually what your TCP connection binds to. So when you specify an Azure file name, like the one that I gave, which is the fully qualified domain name of davidgowest.files.azure.net, and then a share name, the DNS translates that into an IP address, which is actually an IP address that's shared among a lot of different shares. And then a software load balancer directs that to one of many front ends, usually 300 or 400, that's within what's called a single tenant. And it hashes the TCP header, so it's effectively random. So it just randomly picks a different front end. And so each new connection, even from the same client, goes to a different front end. And then those front end nodes are what contain state associated with the connection, some credits we're able to do, things that can be transient, things that don't have to be durably committed. We're able to go and store those in the front end, just in memory in that case. And the back end nodes are these EN nodes are the ones that actually have the data. And I show here on the lower left the back end table node, and that would be for, if you open a particular share, that would be the node that right now is hosting that share. But then the data for all the files in that share are spread out among many EN nodes. So there is this one bottleneck for a particular share of a single Xtable server that allows us to do the transactions for metadata operations in a non-distributed way, because distributed transactions are slower and harder. And this is a way that we can still have really good scaling because, again, you connect even the same client making multiple connections, or multiple clients all connecting to the same share, all go through different front ends. And then the actual file data is spread around among multiple EN extents, EN nodes, which are the ones who read and write these things that we call streams, which is the low-level data. So the active clustering availability that we get is really the result of persistent handles, which I delve into a little bit later. But the idea that this state is completely durable, that you have the fact that you had a handle open. So when you open this handle and are read or writing a data, we know what the byte range locks, we know what the state of the lease is. All that stuff is durably committed. So that when you basically disconnect and have to reconnect again, there's no difference in terms of what your contract was with the server that you're talking to. It looks like you simply had a bit of a hiccup. And especially since all of the DNS name all translates to the same IP address, you're still talking to the same IP address even. Now, when you reconnect, you'll get a different front-end node, because many of the reasons you'll get disconnected is because we're doing a software upgrade. And when we do a software upgrade, we go and shoot each FE in the head so that we can go and upgrade its software, and then its connections go somewhere else. And this is happening all the time, and it really is not noticeable. Okay. And anyway, so that's what allows us really to have this ability to have multiple different connections, all reading and writing the same data from the same files at the same time and have it scale out. So when we were doing this, the idea is that we wanted to, durable state's more expensive. And so anything that we can keep in memory in the front end is great, and that we can cache there. And there's even a few things that are not associated with the ephemeral nature of the connection. Things like the file ID can't change. If something is a directory or not, can't change. Not a whole lot else, but there's a few things that you're actually able to cache on the front end that basically allow you to have a little bit faster operation. This is something you probably already know, the SMB being a stateful protocol. One of the things that also made persistent handles much easier to implement is that the client maintains some of the data across these reconnects. There's a crate GUID that happens, because certain operations are once only. They're not idempotent. Things like supersede overwrite. You can't do that more than once, or create, because there's a crate if or open if. Crate. Yeah, open if means open it or always open it, and then create means fail it if it's already there. Obviously, you can't do that more than once because the second one will fail, and it's very difficult without help from the client to know whether or not this is the first one or not. And so having the client just carry some of the load by passing this crate GUID really helps us. And we're able to go and do this relatively seamlessly because we know that when we record this crate GUID with a handle durably, and therefore if we get another one and it's the same crate GUID, we say we just succeeded. Because what that means is that we did the create, but something went wrong and we never got the answer back to the client. So the client reconnected, sent the exact same message down again with the same crate GUID, and then we know we've already done that. And so, again, and the client is none the wiser. There was a slight delay in this crate, but otherwise everything just works. This is an example of showing how reconnects work. You have, again, the load balancer, someone specifying a DNS, a fully qualified domain name that goes through DNS, turns into IP address. The software load balancer then basically randomly picks one front end who then goes and does their communications with the table and blob store below it. Somewhat of a recap here of using the tables so that we have our durable and persistent metadata state for all the different files and operations and leases and byte range locks and all that sort of stuff. What I currently said is a one-to-one correspondence between shares and partitions, currently. That means that it allows us very easily to do transactions across them, but it does have some implications of scaling, because it means at any one point, there's a single server who is maintaining the metadata, all the metadata for that share, which is why things like read and write scale much better than create and close, because reads and writes, you're able to go and just directly send them from one random front end, again, to one of many stream nodes that are at the very bottom. And that's able to scale really well, whereas metadata operations don't scale as well. So this will show what happens when a disconnect goes on. You have two clients, both accessing the same share, potentially the same file. They got randomly sent to different front ends. And one of them loses a connection for any number of reasons. So then it automatically connects to a new front end and then just picks up where it left off. Before we had persistent handles in SMB3, we had what were called durable handles in 2.1. And durable handles weren't as good as persistent handles. They weren't designed to be. They were designed only to handle network hiccups and not full server crashes, where persistent handles were part of the Microsoft clustering that were designed to handle that. So we actually were able to leverage persistent handles to get the completely seamlessness, but even with durable handles, it's still pretty good. But there are some cases where you don't get the seamlessness from them. Some examples of the state tiering that I talked about earlier, about how we have different obligations for durability based on the kind of state it is. And again, things like if you're familiar with SMB2, there's what they call a file ID, which is really a handle ID, has two components. One is a durable value, and the other one's a volatile value. And that is volatile is only valid for that particular session. And so if you have a session that never outlives the connection to that front end, so there's no reason to store that volatile ID, because if you reconnect to a different front end, those will all be brand new. It's a 64-bit persistent ID. That's what's important. That has to be stored, and that's what we do commit durably. So we have the state that has to be durable. Just for it helped me in thinking about it, and the way that we talked about solid and fluid durable state. This durable state that the user can't directly assign or change, things like a session ID, that we still have to durably commit, but the user really has no control over it. Whereas there's other things like timestamps and file sizes, which also have to be durably committed, but the user can just set them. And so if you're considering in terms of performance or how you're going to potentially tier these further, you can basically make some assumptions about how often things can change, because this this solid durable state is things that only we change. And so we have a lot of control over how we do that. Whereas the fluid one is just normal file system metadata that you're very familiar with. Because the session ID is how you reconnect, right? So when you store the previous session ID. So when you send a new session setup command, you return the previous session ID, and that allows me to know that I'm going to restore all these handles from the old session. Because every session setup command supplies the previous session ID, and that way I know that this is the same client reconnecting. I'm sorry. By the way, the question was, why do we care about the session ID? No. And this is a difference between persistent handles and durable handles. Another reason why why persistent handles are better. Durable handles get reconnected on use. And so what that means, and also when a session disconnects, these things get set on a timer. Right now the default time is 2 minutes. And so if you don't use that durable handle within 2 minutes, it gets closed. And we saw cases before we implemented persistent handles where it would be some handle to a log file or something. And then there was a disconnect. And then a week later, someone tried to write something with the log handle, and the app crashed because it failed, because it had been forcibly closed. Whereas with persistent handles, it's right after the tree connect, it goes and it runs through the client, reopens all of those handles. So we get the reopen really quickly.
But it's still the client who does that.
Yes, the client does that. But it does it invisibly to the app. So the app doesn't know anything happened. This is all happening under the covers. So that I can identify that this session is reconnecting. Because by having the previous session ID, I can know that this is the same client reconnecting to that session. And it allows me to basically go and yeah. I don't think it's just an optimization. I'd have to think about it a little bit more to think about it. But I don't think it's just an optimization. I think it's actually really critical.
It's interesting, but what you're describing is very similar to when the trains of thoughts we're going through when we're implementing these things in global handles, etc. in Samba.
Mm-hmm.
So the session ID usually you have the session reconnected.
Yes.
Actually, the session is drawn down.
The session, it's a new session, and it will almost always be on a different front end. Because again, the TCP headers is hashed.
Maybe we should take a call.
Normally, the previous session ID is being used as a state fence that allows you to identify the old session and tear it down. So
Yeah.
very safe if you're wondering to fix this. But there's no reason you couldn't use it as a hint to sort of pre-cache where a client's likely to reopen files, because it is basically the client approving that that was a previous event.
Yeah. So
The main requirement from that is that that's your case to disconnect the old handles and drain out the operations, so you don't have operations running from two locations at the same time.
Yeah, well, we send also when we get that session set up, we do send a message back to the other FE for session disconnect, but that's almost kind of an optimization, because the fact is that as soon as those handles reconnect, then we have a sequence number we update, and so all of the old handles become invalid, and the session can try and do the old session handle, the old FE can try to do something with them, but they'll all fail. And that has, whenever, if you have a normal disconnect on the FE, when it gets a disconnect event from the network stack, it goes and does pretty much the exact same processing as when it gets one of these notifications that said that your session's connected somewhere else. Okay. So again, this is, so one of the things we were able to do with, again, durable handles were intended for network reconnects, because in our case, the DNS name maps to the same IP address. Even if one of our services go down, it looks just like a network disconnect as far as the user is concerned, because nothing else has changed. So we were able to stretch durable handles beyond what they were originally intended for, though the spec required that you have a handle lease. And so there were cases where we could have fully reconnected the handle, but by following the spec, we had to fail that and not allow the durable reconnect because there was no handle lease. And things like byte range locks can go and mess that up as well. So that was the state we were in with SMB 2.1, but we knew better things were coming, so we didn't try to push that any further than we had to. And we had persistent handles coming. And this really allowed us to go and do what we wanted in the first place, which is have it be absolutely seamless. If you look at it philosophically, kind of what a redirector is doing is trying to present the illusion that remote files are actually local. And to do that as well as you can, given certain trade-offs, because when the files are remote, if you want absolute consistency, it becomes very expensive perf-wise. But if you want good performance, and you usually have consistency compromises to make. And leases are an attempt to go and just squeeze out the most efficiency we can while still maintaining that consistency. But that is the ultimate goal. It's always been the ultimate goal. Is that you're redirecting. It's a redirector. You want to present the illusion that you're actually working on local files as much as you can. And if you look at the history over the last 25 or 30 years, it's gotten better and better and better. It used to be that you had to reboot your machine if you had a disconnect. I mean, way eons, going back to DOS or something. It was really bad, or if your system didn't even crash. And now we're to the point with persistent handles that hopefully your app doesn't even notice anything happened. It just continues running. And that's kind of where we wanted to get, the promised land of this. So now we've been doing this now for about 2 years, starting with 2.1, and it's been kind of an illuminating experience because you have all these ideas of how things are going to work, and then once you start getting many customers and many petabytes of data, that is like, wow, it's actually certain scales and certain things you didn't realize were going to happen start happening. Metadata operations are more common than we had wanted or hoped. We have some applications where people had only run them on local file systems. And so we get this a lot where we get a call from a customer, it's like, oh, it's not working well, it's slow or something, and we try, have you tried running it against a local file server? And it's like, well, no, I just ran it on my local system, and then the next step was going to Azure Files. And it's like, well, if it doesn't behave well against a local serve2.sys system, it's going to be even worse for us. And we had some applications that it was like 99.38% of its requests were opens and closes. And that wasn't great on a local NTFS drive, but the fact is it wasn't that bad. It wasn't enough to be noticeable. But now with each one of those operations, which might take 20 or 30 microseconds on NTFS, and that turns into 10 milliseconds, that's a big, you can notice that one a lot. So we originally, we realized that some applications that were never even intended to be run over the network have problems being directly run against Azure Files. And we also have a specific problem with write-only handles that I'll get into a bit in the next slide. Oh, actually, the next slide after this one. But one of the things when we actually look at the breakdown of different requests, that you realize that there's 4 commands that really are all of the total request count and all the total request time is open, close, read, and write. And so this is based off a month's worth of traffic, again, based on the June Plugfest. and they're ordered by the biggest down to the lowest on the right side there. These are the SMB create. And it's interesting, the left graph is, oh, I'm sorry, let me get rid of that. That hopefully will help. There we go. So the left side is total percent of SMB request types by total requests. So it doesn't take into account how long each request took, just how many requests there were. And then the one on the right is by total end-to-end time. So something that takes a long time, is weighted more on the right chart. And what's interesting here is you look at us, in terms of total time, it's writes are the most thing, which is since we're kind of a newest service, is people copying data to us. And so what we'd imagine is that as we get more and time goes on, read and write will start more averaging out. But at least in the beginning here, there's more data going into Azure Files than coming out, which is good. And then create and close, make up the next big ones. And then after that, it's just not a lot of contributions. And things that we basically spent lots and lots of time getting just right, things like file locks, byte range locks. There's a lot of really weird semantics that byte range locks have. And getting that all right and getting the race conditions right, because you're satisfying byte range locks and you have to go, send requests back to people that have gone away now and that front end has died. And so I have to know to go and retry it on the other front end. And all the race conditions, all the error paths, it was just, nightmarish, a lot of it. And finally getting it all to work right for, 0.0 whatever it is. It's a very small percentage. But those that do use it actually depend on it. There's an IBM app, which is used, I'd never heard of it before, but it's used some database thing. And a lot of customers all use it. And we've had requests from multiple continents for this one particular IBM app that wasn't working right because of a bug in byte range locking. So we got that fixed. But it's, when you have a particular API that somebody needs, they need it, and their app doesn't function without it. Yes? Oh, and not get it. No, I could generate them though.
I'd be fascinated to know that.
Yeah, because the Microsoft client always requests 7, unless it's just read attributes open. 7 meaning read write handle.
And if the client gets an exclusive lease, they won't send you byte range locks because they
Yeah.
can pass them.
Yes, exactly.
I was just curious.
Yeah, so there could actually people could be using. So by the way, the question was if we have any statistics on what percentage of actual opens are contended. And so we have to do something about leases other than just grant the full read-write handle. The implication is that if somebody has an exclusive lease and they do byte range locking, those locks can be cached on the client because nobody else has the file open, so there's no point sending the locks to the server. So that could be under-reporting here, the actual number of byte range locks in use by clients, which is a good point. So yeah, I don't have that data off the top of my head. But it's interesting. I can include that in a later presentation. This deals with some very specific issues that we've dealt with. The biggest one is leaked handles. So people can't people try to delete a file and it doesn't go away. And the error that's returned, the NT status turned over the wire, status delete pending, and that gets turned into a Win32 error access denied. There is actually a status delete pending, but that mapping couldn't be changed for app compat reasons. Neil probably remembers that one. It was in XPSP2, I think they tried to change it and it broke too many things, which was unfortunate because error delete pending is a much more descriptive, what the problem is. So we get these cases, and one of the things it's motive us to do is we have to have these things be more self-serving. Right now, if we get a case somebody can't delete a file, we can go through our logs, and it takes us time, human time, to go and figure out when did they open the handle that's leaked, what IP address did they open it from, and how have they accessed it since then. And then you give them enough of those clues, and all of a sudden they don't call back and the file's gone. So, so they found out where their leak was and they dealt with it. But that's a really inefficient. It's both inefficient for both us and the customer, obviously. So it would be nice to have some way to go and have that be more self-service. And that was an important lesson learned, is that things that happen that are common sort of mistakes, we've got to have a way for the customer to serve themselves and get lists of open handles or something. or at least for files that are delete pending, what are the remaining open handles? Because usually there should be none. Thanks. Also, people who have local servers are used to being able to do netfile/close, netfile ID/close. So if this is ever a problem locally, you just remote desktop into the server, or you could probably do it over PowerShell these days and just close a handle, right? No big problem. Well, they can't do that with us. There's no way they can do a netfile ID/close to us because we don't do that. And then also locally on a local server, if worst comes to worst, you just yank the plug and plug it back in and restart it, and that usually fixes most server problems, right? There's no way they can do that to Azure Files, so they can't. It's a sense that they don't know what the problem is, and they don't have a lot of actionability on their end or information, and that can be frustrating for them. And then for us to give them that information is very time consuming for us. And this has especially been a problem on Linux for Linux customers because unlinking a file has very different semantics than in Windows. You can just unlink a file if there's open name, if there's open handles on it. And so people are taking an app that worked perfectly well talking to Samba on Linux, and then they try running it into Azure Files, and they run into these problems. And so that's become an issue. Yes?
But you do have that data in the tables. So
Yeah.
theoretically, you could make it
No.
available on a web
Yes.
page admin.
We could. It's just the number of hours in a day, and it's on the list. I mean,
It's a web app. Get someone else.
Yeah, so believe me, it's raised, it's percolating up because of the actual real cost. The other point, I'll talk about write-only handles. Our nemesis has been the append open mode for Fopen, because it opens a write-only handle. And the problem with write-only handles is that the way NT works on the cache manager, it's a virtual demand page cache, which means that if you don't request read access locally, that's fine because you just don't validate those pages to user mode. But when you're going over the server, you're having to fault in whole pages. And so the server knows that you didn't have read access. So it can't send those back to you to populate your buffer cache. So what it means is every write has to go over the wire. And if you have a badly behaved app, we had this one app called BinPlace that was part of our build system, which wrote like 20 or 30 megabyte files, and it did them one extending write byte at a time. So it fopened append and did fwrite, 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 20 million times. And so that's bad enough on a local file system, right? But not enough that you might not notice if you only run it a few times. On a remote server, when it gets to server2.sys, it's still all cached. So it's still pretty quick, but on us, it's just brutal. Not only are we writing to the handle, but we're also going and doing the commit of all the data. So it's both an extend of the file and writing the data. So please, please, please request read access. We had one Linux developer that told me that they were philosophically opposed to requesting read access because they didn't intend to read from the handle. Which is, I guess, it's a valid argument, philosophically. But from a practical point of view, please request read access. Variabilities in performance has been an issue where noisy neighbor problems. We had another customer that they really wanted to run Azure Files, but we just weren't able to give the consistency of sure, on some really unloaded tenants who might get down to 3 or 4 milliseconds for open. It really does happen. It's pretty amazing we can do all that in 3 milliseconds. But then some other tenants, it can be really bad, and it can be 15, 20 milliseconds, and then you'll have this weird outlier of 3 seconds because some partition had to get reloaded, and there's a bunch of other stuff happening, and so that got delayed. And for a lot of applications, that's just, they can't have that. So the outliers in latency are what's most important. And so we're working on that as well. Shared namespace, I mentioned before, that also had some implications in terms of reducing what you can call files. And so far it hasn't been that bad, and there's not a lot we can do about that if we want to maintain this shared namespace. Last point is generally poorly written apps. And it's, what's nice about files is they're stateful. So don't keep opening the same state. Open a handle and do what you need to do with it, and then close it. Don't assume everything is name-based because that defeats the whole purpose of statefulness. And there's not a lot we can do about that either. We just have people write better apps understanding this, because what is kind of a little bad locally is kind of a little more bad talking to server2.sys can be very bad talking to us. And just getting people to run Wireshark and look at their traces and that's it. I have 5 minutes. So 5 minutes, I'll open up to questions. I think that's a hint, but you did say 5 minutes, so I don't know. Yes?
Yeah, do you see demand for higher performance on the
Do I see the what?
on the higher performance?
Yes.
You mentioned 60 megabytes a second, 1,000 IOPS. Do you see demand and plans to higher performance?
You know, again, it's not so much the latency, and those are fine because people can go and create more shares if they need to, and get higher throughput and more IOPS. And so there's workarounds for that. The problem is this variability in performance, which we don't have a workaround. I mean, telling people, well, go and start, run on a very lightly loaded cluster. Well, 2 months from now, there could be a heavily loaded cluster, and then they're stuck. So that requires longer-term engineering to fix the variability problem. The one thing that has been an issue is the 5 terabyte share limit, which is causing problems for some customers, and also because we didn't do not the DNS, the one that has the symbolic links on share names. I forget what it's called now. I can't. And DNS? DFS, thank you, DFS. So we didn't do the DFS ioctls to actually implement basically what is effectively a tree through symbolic links to create the illusion of larger shares. In hindsight, I kind of wish we had, because that would have at least been a workaround for the time being until we can get larger shares online.
Doesn't the new thing that was talked about earlier, the redirect, does that help you?
The new thing
Sorry.
that Matthew talked about?
He wasn't in the talk, so
Sorry. Yeah.
but I don't think it matters because for you, your load balancer tells the client which IP is
Yes.
on the back end.
Yeah.
So this doesn't apply.
Yeah. And again, that IOPS limit per share is per share. So even if you're coming in from 10 different clients, it's the aggregate in that share, not per client. And the one thing I forgot here too, so I still have 1 minute left maybe, is the number of handles. We limited that to 1,000 just because we figured who would ever want to open more than 1,000 handles to a file? Because each one of those handles is for us a separate row in a table, and they're expensive. And then again, it goes back to the leaked handle problem, and most of those handles are root directory handles. People open the root directory, and yeah, I guess it's morning, so it's time to go. All right, well, thank you very much. All right.